So welcome to High Fidelity Block CAD. My name is Orion DeYoe. I'm the mentor design lead for FRC Team 3005. I was an FRC alum. I was a student for 4 years when I was in high school. I also mentor FTC for a variety of teams, 3005 and before. I'm the mechanical engineering manager at Rev Robotics. So that's a quick overview of what we're going to talk about today. I've got a few notes I'm going to start off with, just to kind of some context for this talk. Then we're going to talk about very briefly about the block CAD process that 3005 uses, what that means, like what I mean by block CAD. Then I'm going to kind of give a pitch of like why I think you guys should use the process that 3005 uses. And then towards the end, we're going to go through in a lot more detail about how to actually implement it. I have a ton of content in this slide. This is kind of a long presentation, so I'm going to go really fast to try to make sure we have some time for questions at the end, but we're probably going to be butting up right against the time limit. So if I only have time for like 1 or 2 questions at the end, I'm going to be sticking around for a little bit after the session. If you guys want to come up and talk to me, you can ask more questions kind of after everybody's leaving the room if you need to. So yes, we'll post the slide deck. We're also recording this whole thing. So, you know, be careful what you say, mainly for the people in front. Okay, so a quick note here, keep your goals in mind. We're going to talk about a lot of specifics and a lot of processes and things. And whenever you're talking about a process, it's important to keep in context what the goal that you're trying to accomplish is. So your team is going to have different competitive goals to the team next to you, and it's going to differ year to year. And so how you implement this process and how you go about your design process in general is going to depend on what your competitive goals are. In addition to that, we're going to talk about CAD specifically today and the design process. So keep in mind, what are the goals of the CAD phase of your build system? Like, what are you actually trying to accomplish? Just kind of keep that in mind. 3005 uses Onshape. A lot of the processes that I'm talking about today are kind of specific to Onshape. There are several specific tools that I've got, you know, listed here that are specific to Onshape that make this process work better, but there's no reason that you can't use this process with SolidWorks or Inventor or Fusion 360 or any other CAD program of your choice. Okay, so let's talk about what does 3005 do for block CAD. So we start off in early build season, we start off with a layout sketch process. This is where we're kind of doing like a side view of the robot, usually maybe a top view, kind of a skeleton of the critical geometry that the robot has, you know, maybe arm joints, you know, elevator displacement limits, roller locations, things like that. 3005 is not doing anything particularly unique in this regard. I'll go a little bit more in detail about some of the tips and tricks I recommend for this process, but this is pretty similar to the process that most FRC teams use. Then what we do is we move into this 3D block CAD phase after we're done with the layout sketch, or mostly done with the layout sketch. It's a simplified 3D model of the robot. It lives right on top of the layout sketches, so it's modeled in the same part studio as all the layout sketches are. We're tying the geometry of the block CAD to the layout sketches, so roller locations, arm pivot points, all that stuff is attached to the layout sketch skeleton. We're not defining that critical geometry in the block CAD. And then the big thing too is like each subsystem or like kinematically separate piece is its own part, right? It's just a lump. And we'll talk about the reasons for that why later in the presentation. And then, yeah, we're just color coding everything. Really nice, a really nice way to visually tell the difference between different subsystems and things like that. The big difference between the way that 3005 does block CAD and the way that a lot of other teams do block CAD is the level of fidelity that we're putting into the model. So you see here a couple examples of subsystems from the past couple of years, and we're adding in features like belts and motors and gears, some shafts, realistic structural dimensions. You know, the plates that you're seeing there are modeled to the actual correct thickness of the polycarb or whatever it is that we're using. We're not kind of estimating or just typing in numbers to space claim. We're actually modeling to the exact locations where those components will exist in real life. And then we're figuring out all of our center to center distances and actual powertrain layouts and stuff at this stage, not at the subsystem level or later in the design process. So the locations that you see where all those gears and belts are, those are the exact locations where those are going to exist on the final robot. After we do a block CAD model in the part studio, we do a block CAD assembly. This allows us to just use mates to kind of like locate everything. This is where we can create a model that you can click and drag and move it around, which is really nice for just kind of demoing the concept. We will generate multiple of these at the early part of the season, so we'll be comparing concepts and things like that. With these assemblies, it's a really hands-on way to kind of demonstrate how the robot's supposed to work. You can also drop it into an assembly of the field and double check your critical geometry to make sure your reaches and your interactions with the field are what you expect in 3 dimensions as opposed to just in that layout sketch. Once we've finished with the block CAD and we're ready to start moving into detailed CAD, we are bringing the block CAD into the subsystem documents directly. And so the way that we organize things is each subsystem has its own document. That's the approach that I recommend in general, just because trying to model your whole robot in one document it gets unmanageable very quickly. And so each subsystem has its own document. Each part studio where we're modeling parts in that document is getting pieces of the block CAD, subsystems of the block CAD derived into that part studio, and then we're modeling on top of that. So we're not bringing in any layout sketches into any of our subsystems at any point. The only thing that the subsystems reference are the block CAD. We'll go into some reasons why here shortly. So this is going to be some of an explanation of like the reasons why we do this, and also kind of a pitch of why I think you guys should adopt this process. So one of the big things that we're trying to do is we're trying to solve these, what I'm calling how to build problems, and we're trying to solve them really early. So you always reach this point where you're looking at, main manipulators or large structural components of your robot, and you're like, okay, how am I physically going to construct this, right? Is this tube and plate? Is this a sheet metal part? Is this a big polycarb thing with standoffs? Like you've got some options usually, especially when you're talking about just main structural framing of your robot. And you can very easily get into kind of like decision paralysis there, and you need to figure out what the best options are for what you're trying to build. The nice thing about the block CAD is because it's much simpler than your detail CAD. If you want to evaluate, is this a tube frame or is this a tube or a plate and standoff construction, you can iterate on both of those concepts much faster in block CAD than you can in detail CAD. You'll waste a lot of time trying to model both of those in a higher detail kind of environment. But here it's, an hour of work or something like that, right? Much faster. The other thing too is that generally, in my opinion, people don't generally figure out their powertrains early enough, especially if you're building a relatively complicated robot where the space that those powertrains take up, they have to everything has to wrap around each other and everything. Figuring that out in the block CAD is really nice because you can make sure that you've got plates and stuff in the right places where you need it to be able to pick up shafts and bearings and actually make your powertrain work the way that you want it to. Having a robot model early in the season, and by a robot model, I mean a relatively accurate, visually representative model of the robot your team is going to be building. This is really good for communication. You generally are going to have this problem where like you've got a whole team of 20, 30, 40 plus students maybe and mentors. And a small fraction of them are probably involved in the actual CAD and design process. And so it can be very hard to maintain team momentum through that first week, 2 weeks, even 3 weeks of the build season, depending on how long your design phase is. And so getting this block CAD model, especially one that you can click and drag and move it around, is really good because you get buy-in from your whole team on the concept of the robot you're building. And it might take you 2 more weeks to build out the detail CAD and get a final model of the robot. But this block CAD model is done much earlier than that. And everybody can kind of be like, yeah, this is the robot we're building, and keep that interest and that hype and that excitement going. There's some other practical things you can do with this. You can use the models to as a, like load them into, VantageScope or whatever to like show your robot as you're doing simulation for your code. You can have that robot model earlier. Something we did last year and a little bit the year before was we actually were using, we were estimating the mass of those blocky subsystems. We were kind of just defining some fake density and saying, this is about the approximate weight distribution. We're using that to get moments of inertias and things like that, and then fed that over to software, and they were able to do a really, really rough PID tune before anything was CAD'd for real. And that's useful for simulation. And it also gets you a little closer when you're doing bring up, where you've got some like PID values that are pretty close, and you're not going to break something the first time you power the robot on. And then there's a couple other things, you can, having a visual 3D model of the robot helps you plan wire paths, even if it's just like taking a screenshot and marking it up with, paint or something like that. And then maybe you might make a model of it, right? You might 3D print out that model so you can physically hold it. Another reason to do this high fidelity block CAD process and drop the block CAD into your subsystems and reference the block CAD instead of layout sketches is it generally makes your entire robot model a lot more stable and a lot less prone to having really problematic errors. I don't really have a slide for this, but I wanted to take a quick note and just say, like, if you're CADing and your number one goal is to avoid ever breaking any geometry or ever having any errors, that's not actually the correct approach. You're going to have geometry break when you're making a model. That's a normal part of the CAD workflow. And getting better at CAD and getting better at design is going to involve just learning how the model is going to break and then how to fix it. And that is a very integrated part of our workflow here, is that I'm not expecting the model to never break. I just need it to break in a way that I can reattach geometry or replace constraints very quickly. And the block CAD really lends itself to that, just because attaching and constraining to sketch geometry generally is pretty unstable, because you're attaching a lot of points as opposed to tangent and coincident constraints, and that gets handles that a little bit, handles connections between center points and stuff a little differently than like connections to edge lines and things like that. And then the other thing too is when you're working in a sketch, especially a complicated layout sketch, a lot of times you're going to be just deleting lines and stuff. And then once you're deleting those lines, you've lost that internal ID, and then that's going to break a lot of stuff down the entire chain. Anything that's referencing that layout sketch would break. Whereas with the block CAD, you can fix the block CAD, and then all of the references to the block CAD stay, healthy. If I know this is a super niche reference, but if you're familiar with the MVVM like template for software development, this is basically the like CAD version of that, where you've got your model and your view, and then you have a translation layer effectively in between. That's kind of what the block CAD is acting like. Another thing here too is in terms of just having an organized model, we're using vehicle space coordinates, where every subsystem is modeled in the correct 3D location where it actually lives on the robot. Each subsystem doesn't have its own origin that's arbitrary. The origin is the center of the robot on the floor for everything. Another reason to do this block CAD process is it does a much better job communicating what each subsystem has to do, what components it needs to have, how much space it's allowed to have, how it's physically constructed, than a layout sketch does. The block CAD is capturing all of that really well. You don't have to worry about guessing about where other subsystems are and things like that. You've got a 3D model that is claiming the space that subsystem needs to have, and everybody is very clear about where their subsystem can live and where it can't. New CAD designers have a really hard time taking a very arbitrary sketch or hand drawing or something like that and turning that into a 3D model. And so having this better visualization, better communicate what a new designer is designing will help them make progress a lot faster, and will help you onboard new CAD students in a lot more of a like smooth way. The other thing too is like, generally speaking, you're not training them on like, here's how you calculate belt center to center distances first. Like, you kind of want to just get them into CAD, get them comfortable modeling a couple of parts. The block CAD workflow makes that a whole lot easier, because you're able to just tell them, here are where the 2 bearing holes go. You don't actually need to know why that gear center to center is what it is. You can just focus on learning the CAD and modeling the parts, and they can learn the more detailed math side of things later. This is tied closely to the stability of the model, but making really big changes that affect multiple subsystems is a lot easier with this block CAD process, because A, the model is just not going to break as much, and B, because you've got a lot more definition in your block CAD. If I move like an arm center position or something like that, that will just update across all of my subsystems relatively easily. And yeah, and I got a couple examples there of like things that you might change on your robot. These types of big structural changes are very common in a really detailed mechanical design, and so building those in and being able to make those changes without breaking is a huge advantage. Kind of a reminder of like, what are the key objectives that you're trying to do during the CAD phase? Like, what are you trying to hit? You're trying to solve the geometry of the robot. You're trying to figure out how to build problems, like I said, like how things are physically constructed, trying to figure that stuff out. And then you're trying to communicate it's kind of like what the way that each subsystem needs to be built, essentially, and what the limitations on that are. And so it's important to just keep these objectives in mind during the block CAD process. Okay, so now we're going to get into kind of like how to actually implement this on your team if you want to. So the first thing you need to start off is you need to have somebody that's responsible for this. This is not the only person that will work on the block CAD. More than one person can work on it, especially in Onshape. But you need to have somebody that owns it, because this is a kind of a single point of failure. So like, if your block CAD breaks apart and has errors or things that are, features that are not building or whatever, then that will affect your entire robot model. So you need to make sure that your block CAD is always in a healthy state. You need to be doing your version control and everything in Onshape to make sure that the most up-to-date version is pushed out. Versions that are incomplete are not pushed out to the individuals designing subsystems. The person that's owning this, like I said, they're not the only person that's editing it, but they do need to be a very experienced CAD user. I recommend it being either a mentor or a student that's got a lot of design experience. You're not always going to have a student that is capable of doing the level of like detail CAD that you need here. And so it may just change year to year who's managing it, and it's going to differ team to team too. In terms of how you kind of divide up the labor, like the block CAD process is a little bit bottlenecked. And so the way that we do it on 3005 is most of the team is working on other things, while even the CAD people are working on other things while this is happening. We do a low to moderate amount of prototyping, but most of the prototyping we do is using CAD models. So we're laser cutting or CNC routing parts for prototypes. And so we've got CAD students and CAD mentors working on those prototypes, and those prototypes are informed by the geometry of the block CAD. And then that also cycles back into, as we tweak roller locations and things in the prototypes, that then informs the geometry of the block CAD back and forth. And so that's kind of how we keep everybody occupied in the first part of the build season. And just a reminder on that lesson, like it is, even though layout sketches and block CAD are the first part of the design process, that's not the first thing you should teach CAD students. Like this is an advanced skill. So new CAD students should be focused on learning the software, modeling individual parts that then get manufactured, so they get to close that loop on, I model this thing and then it gets made on this machine, and they can get that understanding, and then they can learn these layout sketching skills, after a couple years of doing CAD maybe. going back over it, this is going to go into more detail on some of the stuff that I talked about originally. So there's a little bit of redundancy here, but we have a separate document for every robot concept, and we have multiple of them at the beginning of the season, right? Because we're just exploring our options and things like that. Is we just have a folder of like concepts. Each concept is its own document. We have a template that we create with the field elements already built in, so we don't have to remodel like side views of the critical field elements. You can see this is like this a view of, you know, the trap and the amp and the speaker and stuff from last year. And we generally I'll go into a little more detail on that a little later. I already mentioned the layout sketches and the block CAD are in the same part studio. Keep that feature tree organized. There's going to be a lot of stuff in that feature tree. A couple specific things. Make sure all the layout sketches are at the beginning. Don't bury them in the middle of the feature tree. It just makes organization impossible. And it also gets really hard to manage what's constrained to what and whether you can reorder things. Just keep the layout sketches at the beginning. You'll have a much better time that way. I also recommend grouping your block CAD features by subsystem. So like, don't model a part for the intake and then a part for the superstructure and then a part for the launcher and then come back and model the side plate for the intake. I don't recommend doing it that way. I recommend just like every feature for the intake all in one line, if at all possible. It's not always possible, but it usually is. And generally speaking, if you find yourself in a situation where you feel like you need to model part of a subsystem, model another subsystem, and then go back and finish the earlier subsystem, if you find yourself in that situation, generally that means you didn't put enough detail into your layout sketch. That's generally what that means. So the other nice thing about having these like big groups of like, this is everything for the intake all in a straight line in the feature tree is you can then just delete that whole subsystem and remodel it, and without having to hunt through the feature tree to find all of the different features for it. And you will do that frequently during the block CAD process. We break our layout sketches up into multiple sketches. Not everybody does this, but this is the way we do it, and I do recommend it. It lets you show and hide different kind of like layers of what you're designing. It allows you to put a lot more detail into your layout sketches too, because you're not cluttering up one sketch with like 5 million pieces of geometry and constraints. I recommend modeling just like at the beginning of the season, model a layout sketch template that's got just like the extension limits, bumpers, drivetrain components, because generally these days with Swerve, you kind of know what your drivetrain is 2 seconds after kickoff. We model both field elements on like the front side and the back side, because we don't know what direction we're going to be approaching the field elements from necessarily early in the process. And then, yeah, every subsystem gets its own layout sketch that's just kind of layered on top. And then if we have to have something that's really complicated and really integrated, then it'll get combined. A couple of rules that we kind of follow here. No unconstrained geometry in your layout sketch. One thing is that sometimes what people will try to do is they'll try to use their layout sketch the way that we're using our block CAD assembly, where like they want something they can click and drag and move around. That's not really what the layout sketch is for. If you're doing that early in the, like you haven't gotten that far into the layout sketch and you're leaving stuff unconstrained so you can drag it around, that's fine. It's just by the time you get into the block CAD part, you need it to be fully constrained so you don't have any weird stuff moving around on you as you're doing updates and changing dimensions and stuff. The way that we do it is we are drawing the same mechanism in multiple positions, and then we're linking those two things to each other using like equals constraints and length dimensions and stuff like that. And that's allowing us to use constraints to kind of figure out, okay, well, the launcher has to be below this height in this position, but it needs to clear this other thing down here. And we can apply all those constraints. This is a pretty normal layout sketch workflow, but just kind of calling these out here. And then, yeah, you're starting your vehicle coordinate system here. Origin is on the ground in the center of the robot, left to right, front to back. That's pretty standard. Highly recommend you stick to that coordinate system. pretty much everybody that's doing vehicle space coordinate stuff in Onshape is doing it that way. I think it's a Spectrum that had that standard originally. All right.
We still have 1678. So
Okay. All right. It's been standard for a long time, so I think most people are doing this. But if you're not doing it, I recommend it. Yeah. So when you do the block CAD, you're gonna have to pick a position to model the parts in. There's basically two good options. You can draw it either in its starting configuration or pick some nice orthogonal like angle to put the mechanism at. Our robot for the 2024 season was modeled in the starting configuration. The 2023 robot had the arm in that horizontal position just because having it horizontal just made it kind of easier to model things aligned with the origin axes. You'll add some extra sketches, some extra layout sketches to plan like more detailed geometry, or at least I do personally. That's not an absolute requirement. You can just kind of go into the block CAD and figure it out as you go. But I will also sometimes add some like hybrid layout sketches that are not really a layout sketch and they're not really block CAD. They're kind of in between. That's more just personal preference. Keeping all the parts as keeping everything in one subsystem as a single part is really important because it means you won't forget it later when you're deriving those parts into your part studios. So sometimes we'll add these like little like tabs and stuff on parts that don't actually exist in real life just to keep things joined together. Find a nice naming convention. Usually we kind of put the block CAD in all caps to keep it very visually distinct later, and just very descriptive names for what each block CAD chunk is, right? And then once again, color coding. So some specifics here. If you've got a tube frame, you're just modeling those as solid rectangular blocks. Doesn't need to be hollow. Most of the time, you don't need the brackets. Motors or cylinders of the correct size. Gears are also cylinders. Make sure you're modeling those as the actual tooth outside diameter, not the pitch diameter, because you want to make sure that you've got the correct clearances for all your powertrain components. Don't model anything smaller than it actually is in real life, because that's where you're going to get into trouble in terms of having the correct space claims. And then, yeah, sometimes we'll model shafts as needed. I'd usually just model them as like the 13.75 millimeter round if it's rounded hex, or if it's got like spacers on it and I care about the clearance, I'll model whatever the spacer OD. We usually 3D print our spacers. So I think it's usually 3/4 or something. I don't remember what we use, but we have a standard. We're kind of doing these. You'll see a couple of these like these simplified belts I've shown in a few of these screenshots. Obviously, there's no cylinder there to represent the pulley. It's just the belt itself. The belt is actually modeled not at the width of the belt. It's actually modeled at the width of the pulley, because we're just claiming that space and trying to communicate where those center to centers of that belt live. And so that's one extrude feature. And so you don't need to put any more detail into it than that. That captures the full design intent that it needs to capture. Gears, same way. They usually have those little bearing bosses so that the adjacent gears don't rub on each other, but you could just model them the full face, or more than the full face width up to the bearing bosses. That's pretty straightforward. If you need to capture like spacings with bearing flanges or everything, you can see in the top right, we've got that little like boss sticking out that's representing a bearing, and we need to make sure that we're having clearance for that with other components. The other thing too is we're not really doing a lot of sharp edges or jagged edges. We're using a lot of rounded curves at the perimeters of parts. And the reason that we do that is that gives us a really good place to use like a coincident constraint or a concentric constraint or something. And those rounded curves, like on these gearbox plates in the lower left, it's implying a pivot. It's implying a shaft center in the center of that arc. And so it's just, we're using less geometry to communicate more design intent is essentially what's happening here. And then the block CAD assembly, a couple tips here. Once again, in the same document as the layout sketches in the block CAD itself, just keep all of that grouped together is essentially what we're doing. You'll sometimes have to add mate connectors in the block CAD part studio to be able to constrain things fully, just because the block CAD tends to kind of have some like very highly representative geometry or floating things where you're leaving components out. We'll talk a lot more about that later. So yeah, adding mate connectors where you need them, using limits on your mates to make sure that you're creating the actual useful range of motion. You can use configurations for mechanisms that have more discrete states where you can just hit a drop-down list and put it in this, state or whatever. Also, if you haven't used the named positions feature in Onshape, I highly recommend it. It's absolutely perfect for this. You can just kind of specify offsets on mates and click from a drop down and it'll put the whole robot in starting configuration or fully extended or whatever states you'll have for your robot. That was especially useful in 2023 when there were like presets for each of the different levels for each of the different game pieces in taking from the feeder station, whatever. Okay, so the biggest question about this whole thing is what do you actually put in your block CAD and what do you leave until later when you're doing detail CAD? So it's important here to make sure that you're keeping in mind the purpose of what you're doing with the CAD, right? You're trying to solve critical geometry. You're trying to figure out how you want to physically build the mechanism out of what materials and structural elements. And then you want to communicate that to the people designing the subsystems in an effective way. Obviously, doing block CAD the way that we do it takes more time. Like we spend more time in block CAD than most teams do. And so if we're going to spend our time that way, it needs to save us more than that amount of time later. Otherwise, it's not worth it. And so that's going to differ team to team. And so you're going to have to kind of find that balance point yourself, basically. But a few guidelines here. So you want to have every subsystem represented in some way or another. You may have some subsystems that are much lower detail than others, depending on how many interferences they are, how complicated they are. But you should have something for every subsystem that's on your robot, so you've got a good idea of the space available for the things around it. You want to have the main structural elements, right? Because you generally have everything for a subsystem mounting off of it, or you may have multiple subsystems mounting off of the same structure. So you need to make sure that structure is represented accurately. You should have your drivetrain. You should put your bumpers in your block CAD. You should put the critical electronic components in block CAD in some form or another, the battery being the main one, maybe also the PDH. We're not always the best about this. Like the battery wasn't in our block CAD last year, but it absolutely should have been. And that not putting that in our block CAD definitely made it harder to package the battery later because we didn't solve that as early as we could have. So that was a major oversight for us. And so then once you've got all that stuff in there, each subsystem, main structural elements, all that stuff, like where do you put extra detail in? Like where do you start modeling gears and where do you leave that for detail CAD? Anytime you've got an interface between two subsystems, either just a mount point or especially if it's a moving joint like an arm or something like that, you want to put some extra detail into that area to make sure it's extra clear to whoever's designing it what that interface should look like. Because the way that we break it up is we'll have maybe one person modeling the arm and then the other person modeling the tower, and those two things need to just drop together in CAD and work. And so both sides of that moving joint need to be very, very well defined for the people designing the subsystems. Anytime you've got a place that's really tightly packaged, got to put more detail in there to make sure that all of that fits. That's the top image there. Our intake this year is kind of like shrink wrapped around all of the different components in our drivetrain. And so we put a ton of detail into the belt pathing, the plates, the mounting blocks, all that stuff in there. We even have some standoffs in there just to make sure it clears other components. And so anything that's tightly packaged, you're going to be better off putting detail into your block CAD. Anything that's like kind of weird or special, like you've got an unequal 4-bar for an intake, you've got some over the center latch or something like that, or you've got some cam somewhere, that stuff where you've got like geometry is very critical to function. That type of stuff you probably want to document well in your block CAD so that the people designing the subsystems don't have to do all of that work to figure out what that geometry needs to be, especially if it relates to other subsystems. And then complicated powertrains that are going to have a lot of components, you should plan those out in the block CAD because it just saves a lot of time later. So where can you leave detail out? If you have components or areas of the robot that are not really going to cause any interferences, or they're far away from other components or far away from other subsystems, you don't really need to put a ton of detail in there. Our launcher was kind of like that this past year. It was sticking out in the sticking out kind of into space, and there wasn't a lot around it. And so there wasn't a ton of need to put a lot of detail into the block CAD there because there was a lot of design flexibility on the detail CAD subsystem side. The only thing that was really important was the overall size, the locations of the launcher wheels, and that was basically it. Like we didn't put the motors in there because it didn't really matter where they went as long as they stayed inside the envelope. Tube structures, you don't need to be modeling in brackets usually. Sometimes you do, usually you don't. And then sometimes you'll have situations where you'll have a component that just kind of implies the existence of another component. So like shafts usually work that way. If I've got a gear that's part of my block CAD, well, I don't need to model the shaft in the block CAD because it's very clear that there's a shaft there to the person designing the subsystem later. Even some gearbox plates can be left out. You can see on the top image here our powertrain for our launcher pivot this past year. The gearbox plates that tie all those motion components together is just omitted completely because there was a reasonable degree of flexibility on where those exactly could be. And then small stuff like fasteners is not needed. All right, so when we're ready to derive in, so if we finish block CAD, we're ready to derive in and start working on detail CAD. The derive feature is just a feature in Onshape. If you haven't used it before, it's pretty straightforward. It just basically drops a part from another part studio into whatever part studio you're working in. It comes along with all the like version control stuff that you would expect it to, where you can drop in certain versions and you can do updates and things like that. Only bring in the block CAD components that you need. You don't need to bring in the whole robot block CAD because you can bring in the individual subsystem parts. You do want to bring in a lot of them usually though, especially if it's a component that's kind of in the middle of the robot surrounded by everything else. You want to make sure that you have the subsystem you're working on and then anything that it interfaces with or has close like potential interferences. Then we color code it. We use this like transparent purple color because it's very visually distinct from everything else that we're doing. It being transparent is also really nice because it kind of doesn't block your view of the real components there. You're going to show and hide these parts a lot. So you should get used to doing that. You pick whatever color works for you. If your team color is purple, you probably don't want to use purple. You probably want to pick something else. It's not important as long as it's visually distinct. Yeah, and then when we get into the detail CAD modeling, a few notes here. You want to attach everything you possibly can to these derived block CAD parts. You don't want to be doing like extrusions where you're typing in material thicknesses into a blind extrude. You want to use like up to face to set the thicknesses of plates and stuff. So if you go and update the block CAD, it'll update your real parts. You should be using as much, as many constraints to the block CAD components as you can, just to link in shaft center distances and shaft locations and stuff like that. You don't necessarily need to follow the exact perimeters of the parts that you model in block CAD. It's just really, you just don't want to exceed that size is really the general guideline. So in block CAD, you'll just model kind of a weird lumpy shape. You'll use a lot of arcs. You can stylize that better, take weight out, do whatever you need to do in the detail CAD. Just try not to exceed the envelope that you've defined for yourself in block CAD. Other than that, it's pretty straightforward. Obviously, I've outlined a pretty detailed process here, the way that we do it. But it's important to keep the goals in mind of what you're trying to do in the season. And if your team has different requirements or the process doesn't quite work for you, deviate from the process where you need to make it work. And then later in the season, where your robot's well-defined, built, you need to make changes based on testing, you're going to deviate from the block CAD process pretty much 100%, because you know the changes need to be made. Most of the robots are already defined. This process is a whole lot less useful later in the season. And by sticking to it, too much, you're just going to add a bunch of CAD overhead that you don't need when you're in between competitions and need to get something done. Our 2023 like gripper intake thing had like over a dozen iterations, and it was after the first iteration we stopped using the block CAD because we knew how much space it had available and we knew the changes needed to get made. So that was just getting direct modeled in a part studio whenever we needed to make changes to it. All right, we have some time for questions. Yes.
You have a unshaped model with cameras to sample.
I do. So our CAD from this season and last season are available. They're linked on Chief Delphi. I had to do a weird thing to like scrub out students' names and stuff from the edit history. So the block CAD is a separate link. But if you go to that Chief Delphi post, there is a link to our block CAD document. I saw a hand over here. Yeah.
So when you're making like upgrades, how do you prevent like a small change propagating? If there's something running,
Yeah.
small change, it doesn't change by like, and then all of a sudden.
Yeah, I mean, that's a tough one. Oh, yeah, sorry. So the question was, how do you, if you are using this process, how do you keep one tiny little tweak to like a shaft location or something from propagating a bunch of changes to a bunch of other parts across the entire robot? There's a couple answers there. So the high level answer is you need to have a good enough understanding of the relationships between all the geometry on your robot that you know what's going to change when you make a change. That is the point of having somebody that owns the block CAD, is they need to understand the constraints well enough that they know if I move the shaft, nothing else is going to move, or they know what else does move. Also, Onshape makes that relatively easy because you do have the ability to only propagate that change through versions to certain subsystems. So if you're like, I want this plate on the launcher to move and I don't want anything on the rest of the robot to move, only do that update on the launcher subsystem. Yeah, and then the third thing I would say there is that also relates very strongly to the way that you do your mechanical design. Several other of the, like in the mechanical talks, people have talked about it, but it's like having a giant plate that's the entire side of your robot that has every feature for intake, launcher, everything is not a particularly good mechanical design practice. That should be broken into multiple separate parts. And if it is broken into multiple separate parts, you don't run the risk of having more changes than you expect. Yeah.
Putting this block CAD into the field CAD at all? Or?
Yeah, so we build that block CAD assembly that we can click and drag and move around. And then, yeah, we usually drop that into the field CAD. It was not as important this year because of launching, but it was very important in 2023 to make sure that the reach of the arm and the angle of attack of like placing the cone on the peg was good. And so, yeah, that's a very useful thing to do.
I might have missed this in your slides somewhere, but I use variable studios for center to center. Those live primarily on.
So the question was, do you use variable studios in block CAD and where do they live? Yeah, we'll use variable studios. Now, the variable studio itself is, it depends on what it is. So like, if it's something that you're going to be using across multiple tabs, then the variable studio is usable. And in that case, I would just create one in the same document as the block CAD and put everything there. We recently, I think we haven't done that. We've only just had variables in the actual block CAD like feature tree. Try to put them towards the top so they're organized. But yeah, and then the idea is that generally you want to rely on the actual geometry of the block CAD to carry information forward rather than variables outside of your document. So I would really try to only keep those used inside of the block CAD document itself. Other questions? Yeah.
How far does it start on book? Like you're talking about like you have multiple sets of block CAD running parallel and actually run
Yeah, so the question was, how far do we go? How far do we go down the process of designing block CAD as we're exploring multiple concepts? It depends on the robot and depends on the concept. So 2023, we spent a lot of time in layout sketch land and not that long in block CAD. This past year was the opposite of that. The layout sketch was not that didn't take that long. The intake geometry was really the only thing that was heavily iterated on. Not necessarily, no. You'll absolutely start working on block CAD before the layout sketches are finished on certain occasions. That was definitely the case this year. Like there was a lot of block CAD features before the layout sketch was even remotely finalized. Like less so in 2023. 2023, the layout sketch was much more finalized before we started block CAD, but there was still quite a bit of overlap. If you're not comfortable using the rollback bar, get comfortable using the rollback bar. You're going to move that thing up and down constantly. Just that is your best friend when you're doing this process. Move the rollback bar around to add features where you need them. More questions? Yeah.
Kind of adding on to that, the general timeline, days, weeks, how long are you working on layouts, block CAD, and then plan CAD?
Okay, so as everybody that's answered this question this weekend said, that's going to differ team to team. We generally can be pretty fast. We can generally have, I need you to help me out here, Rachel, but last year we got stuck on AMP for a long time and that delayed the process. Yes, yeah, exactly. But we can have block CAD starting within a few days of kickoff, but it's not going to be remotely finalized until at least a week into build season.
I would say that we have taken longer to get to the end of block CAD the last 2 seasons than we have previously. So about your team strength. Our team, the manufacturer is in-house. So the exit and use a lot of cost parts. So the actual execution phase is pretty fast. So in the last couple of years, it's taken more time than it normally would to get a better block CAD because then it enabled more students to overlay the geometry on top of the critical features so they can CAD faster. So once we got that block CAD, everything else was faster. So we pushed block CAD deliverable out. And
Yeah.
I really looked it up too, but like I drew at the time, like I was freaking out.
Yeah.
Both years that we had taken so long to block CAD. Citrus had released like 5 iterations of
Yeah.
block CAD yet. So like we just kind of like slow at the beginning, did all the details that enables all the parallel systems on our team.
Yeah, I don't want to repeat that on the mic. Like basically we invest very heavily in the block CAD phase and we let it stretch out a little bit longer than maybe everybody would be comfortable with because we know how much time it saves us on the design and build. Also 3005, just like the way that we build our robots, like physically the parts that we design and like the tools that we use, it takes us like 1 or 2 days to make an entire robot's worth of parts. It's just like the actual manufacturing phase of our season is very, very, very short. So we're okay spending a little bit longer in CAD to make sure we get it right. Other questions? Yeah.
It is that we had a lot of construction line versus solid line. And in the past, people would relate examples like that and they try to extrude it back to real and bad. Like, is there a strategy behind looking at construction line to solid?
Yeah. So 2 things there. 1, try not to extrude layout sketch geometry. Add a new sketch, project, or create new geometry, and then constrain to your layout sketch geometry. That will prevent the like adding holes thing that you mentioned. And then in terms of how I want to like standardize on what's a dotted line and what's not, it just kind of, there's not a hard and fast rule, but generally if it's solid, it's representing something physical, like an actual arm joint. If it's a construction line, it's just representing something that may not actually exist, a relationship. I do a lot of triangulating out things and then using equals constraints to make the triangles be the same size to make mechanisms in multiple positions have the same geometry, even with only 1 dimension. I really don't like having the same dimension on a part that's representing the same part in multiple positions, because if I change it once and forget to change the other, then my layout sketch is invalid. And so I'll use a lot of construction geometry to kind of like tie that stuff together, and that's what those dotted lines are. Yeah.
You touch on your manufacturing capabilities just a little bit that allow you to be so deliberate on your CAD.
Yeah, nothing particularly unique. We've got a 4x8 CNC router, kind of a weird kit one. It's not great, but it's good enough. We've got an Omeo, which we underutilize and should use more. We have an army of 3D printers. We do a ton of 3D printing, nothing fancy, PLA plus for like almost everything. We do a little bit of Markforged, but not much. And then, yeah, I mean, just a lot of COTS parts, pre-drilled tube. Yeah, laser cut. We started using that SRPP material this past year so we can start making more structural plastic parts on our laser cutter instead of on the router. It saves us a lot of time. All right, that's all. We're already over a little bit here, so I want to let you guys go. I'll be here hanging around if you want more questions.